So the name of my talk is the dual nature of consistency in foundation models, challenges and opportunities. So let's just start with the simple question, why consistency? Why should we care about consistency in general in foundation models? So, of course, everyone knows that in the last several years, generative AI got a lot of attention from public. And that's the attention that is both positive and negative. So people are both excited about the models that now only can take several seconds to produce the output that is on the level or even exceeds human capabilities in certain areas, the capabilities of expert humans. So for example, the foundation model can generate the image that I personally wouldn't generate, not even in seconds. I wouldn't be able to do it in years. But on the other hand, models still sometimes show some very basic errors in understanding. And it's quite surprising how these errors could be of a very fundamental type of generalization that seems trivial to many people. So for example, you can see here several examples of such errors. And I will just go through one of them. So let's say here in this dialogue, the user can ask the ChatGPT, who is Tom Cruise's mother? And the ChatGPT answers, Tom Cruise's mother is Mary Lee Pfeiffer. And the next question I want to ask, let's say, is, who is Mary Lee Pfeiffer's son? That would be quite obvious to everyone who is having this conversation, if that's the human. Because if this person is mother of Tom Cruise, obviously that Tom Cruise is her son. But to that question, ChatGPT answers that as of September 2021, we all know that date, there is no widely known information about a person named Mary Lee Pfeiffer having a notable son. So there is a little bit of strange things happening here, right? And this is the type of inconsistency that I'm speaking about, I'm going to speak about today. So, okay, you may ask, okay, sometimes these models do these mistakes. If it's not very frequent, like, why should we care? What? So what? Everyone could be in a slightly unproductive mood maybe sometimes. But the problem here, the way I see it, is that consistency, such a trivial, basic consistency, is usually implied. It's implied by default by human users. And the problem is that its inconsistency instead of consistency is out there quite frequently. And there are very negative possible consequences of that in both the industry and the research. So in the industry, there could be legal, financial, social risks for the companies that are applying this technology. So I think many of you who are local to Canada have heard about legal issue with Air Canada when Air Canada was sued for the bad chatbots advice and was successfully sued. There are other examples that are out there in the news. So companies can have negative, serious consequences. In research, on the other hand, AI models are studied by some researchers for insights into human intelligence and human cognition. And here, obviously, we need to be very cautious because as humans, we do make mistakes, but those mistakes are quite different. Okay, so for me, this topic, this challenge of inconsistency in foundation models, it looks like the elephant in the room because it's a big problem, actually. It's an elephant. And nowadays, when a lot of people are interested in evaluation of these models, in assessing the models, in trying to understand which model is better than another model, thinking about that evaluation quite seriously and putting a lot of efforts into evaluating the models. In this time, at exactly the same time, we just ignore completely the question of inconsistency. Why I'm saying this, that this poor elephant is ignored? I'm saying this because what do you think about if you think about evaluation of large language models, for example? We immediately probably think about some leaderboards, open leaderboards, dynamic ones. And the most popular ones are, for example, the LMC's chatbot arena leaderboard, or OpenLLM leaderboard that is there on Hugging Face, or Can AI Code leaderboard that is used for the code generation models, or Uncensored General Intelligence leaderboard, EQ bench that is used to evaluate emotional intelligence of the models, Alpaca eval leaderboards where models themselves are evaluating other models, massive text embeddings benchmark, open multilingual LLM evaluation leaderboard, you name it. There are many of them. There is a lot of efforts put into preparing and developing these leaderboards. But surprise, consistency evaluation is not included in any of them. At least it is not included directly. So for example, in LMC's chatbot, it's the platform where users can evaluate these systems themselves. So of course, if they see a mistake like that, they would downscore the model. But when you see that some model is performing worse than another one, you do not have that direct connection with the consistency or inconsistency. You do not know why the model, what's the issue, why the model is performing worse. So such kind of evaluation or leaderboard does not help detecting inconsistencies. And I think that there are two main reasons of why this problem of inconsistency is often overlooked. Where the first reason is the lack of agreement on the definitions, and the second one is the lack of agreement on the consistency metrics. At least these two reasons are really like big. Maybe most probably there exists other, but I will speak about those two. So in terms of definitions, even within the research studies that exist currently out there for people who are interested in this topic, in inconsistencies, and are researching that, the definitions are very different across studies. So some people use a very narrow, specific definition, such as, for example, reversal consistency. And the definition is, if a model is trained on a sentence of the form name is description, where a description follows the name, then the model will automatically predict the reverse direction description is name. So you can think about that example with Tom Cruise and his mother. That's a good definition, it's correct, but it is very narrow. And if we want to improve the model based on this definition, we'll probably be able to make some improvements, but they would be quite minor because the definition is too narrow. On the other hand, some other authors have a very broad and generic definition. So think about this. Consistent models behave differently for paraphrases describing the same fact. Yeah, that's true as well. But this one is already quite generic. What are paraphrases? Like, what does it mean to behave differently? What is different enough? what to think about the situation when it is not the exact paraphrase, but for example, the model is prompted on the exact opposite thing, then we expect the exact opposite behavior, right? And if it is not opposite, then it's again inconsistency. And all this is not really covered by neither the narrow definition nor the broad generic definition. Next thing that I have mentioned is the lack of agreement on the consistency metrics. And here again, people use many types of metrics. We do not have something that is very standard for consistency evaluation. Usually it's some kind of a metric that is based on the percentage of incorrect generations, and maybe the combination of this metric with the actual performance of the model. Sometimes it is some adjustments to the loss, so that we have some kind of a consistency loss as an intrinsic evaluation metric. But again, everyone is working with a different type of metric. And it does not help, because if we want to mitigate this inconsistency in language models, and first of all, we need to know how bad or how good we are in our progress. So in order to be good or bad, we need to define first what we want to be good at. And in the end, we do not measure what we do not name, and we do not improve on what we do not measure. And as a result, the mitigation strategy naturally become very limited. Okay, they are limited, but they exist. And I just want to give you a little bit of overview of what kind of mitigation practices exist currently, because that's something that may be quite useful for both ML practitioners and people who are interested in the topic. One interesting practice is to improve consistency is the modification of the standard loss that was proposed by the Elazar et al. In 2021. And they used it specifically for the pre-trained masked language models in the context of recognizing relation between a subject and the object. So quite a narrow context and the specific group of models. So they worked with models like BERT, Roberta, and others. What do they propose? They propose to have the loss that is a combination of the so-called consistency loss and the standard MLM loss, where the consistency loss is just the two-sided KL divergence that measures similarities between the predicted and masked distributions Q for patterns of relations R. So you can see Qn is the predicted, Qm is the masked distribution, and we have a KL divergence which is two-sided. The second part of this loss is the regular MLM loss. And there is also one more part, that small lambda that you can see in the formula, that just defines, it is a hyperparameter, and it just defines how much of each part we should take care of. And this is an effective method, actually. It does work. It improves both the consistency of the model and the ability of the model to extract the correct facts. But it has limitations. Of course, it has limitations. It is limited to a specific type of models, to a specific task, and it was only tested on that semantic consistency that is defined by that broad definition that I used previously, which is about paraphrases. So it was not tested on, let's say, negational consistency or additive, transitive, and there are many others as well. Another mitigation practice that is commonly used is just a fine-tuning. So one of the examples could be in this nice work by Lee et al. Of fine-tuning that the process that has two main stages. One is the data generation stage, where we collect the LM responses, language model responses to some queries and the associated validator queries. So we ask same things in a different ways, in the way that requires the model to generate something and in the way that requires the model to just select the answer from the given list of answers. And then the second stage is to filter only the consistent pairs of these generations and fine-tune the model on this new data. So again, the good thing about this is that no labels are required for this data. And it is fine-tuning, so we can fine-tune for as many iterations as we need. So if we have some metric and we see that the outcome is improving, the result is improving, we can keep fine-tuning until it is improving even more, hopefully. The bad thing is that we still need the human annotations to filter out those consistent pairs, because what? Because the models are not good in consistency detection. So we still need human annotations. And again, as many other studies, this specific technique was only tested on specific type of consistency and only on English data. And again, fine-tuning requires some amount of compute, obviously not as much as we would need with the retraining the model. Okay, up till now, you may have a feeling that inconsistency is just a completely bad thing that should be avoided at all costs. It should be avoided, yes, but I want to give you a different perspective as well, just for a balance, because inconsistency can be also helpful. How it can be helpful? One example. So inconsistency helps the models to reason better. And what exactly do I mean here? I think that many of you have heard of such technique as prompting and chain of thought prompting. The difference between those, okay, I cannot open it to a bigger image, but I hope you can see what is written there. For some context, in standard prompting, you give the model one example of what we want from it. So let's say it's a question with some mathematical task and the answer. And then we give the actual question that we want the answer for. And the answer to that actual question can be incorrect. Okay, chain of thought is a slight improvement to that prompting, because when we give an example of question and answer, it's not just the final answer, but it's some additional reasoning about how that final answer was received. So for the mathematical task, we can explain that first we had so many, let's say, apples, and then we got additional ones, and in the end we got that final result. This technique helps improving the performance, the accuracy of the model. But sometimes it also makes mistakes. The model also makes mistakes, like, for example, in this example, where we do all this chain of thought prompting, and the language model still provides the incorrect answer. The incorrect final answer here is due to the wrong reasoning path that was selected during greedy decode. And here, the idea is it's not just one reasoning path that is out there. As we now know, models are inconsistent, and to the same question, then they can generate many different answers, and here we make use of that fact, of the fact that they generate many different answers that can be different or even opposite to each other. So with the new technique, instead of doing greedy decode, we replace it by sampling from the model's decoder to generate a diverse set, the set of reasoning paths that where each path is different from each other. And after that, we marginalize out the actual reasoning paths and only use the final answers that are the result of that reasoning. And again, out of that diverse set of not that diverse anymore, but still diverse set of final answers, we aggregate it into one final answer that is based on the most frequent answer. And this technique is extremely simple. No fine-tuning is required, no human annotation is required, no additional modules are required. It's very simple, and it turned out to be very effective in terms of improving the performance. It turns out that the fact that the model is able to produce all those different generations, all those different reasoning paths, it may be valuable, actually. You can make use of that, for example, for this purpose. There is another purpose as well, and that another purpose is you can use the inconsistency to calibrate the model. So if you don't know what is calibration, I would just give a very short introduction to that concept. A well-calibrated model is when if the model gives you a correct answer, it is also very confident about that correct answer. If it gives you an incorrect answer, it is not that confident in that. That's a well-calibrated model. But the language models are not, unfortunately, well-calibrated. They can give you incorrect answers and be very confident about that, even though it's completely incorrect. So in order to improve that calibration, inconsistencies can help again. Because why? Because we still remember that there are many different answers, actually, that language model kind of keeps in mind in the background. And it is possible to make use of those many different answers. And before selecting the correct one. So here the authors, Liu et al., in the recent study, they make use of three different ways of, different methods of consistency-based calibration, where the first one is agreement-based, and it's exactly the same as I mentioned before in the chain of thought reasoning part. It's just selecting the most frequent one. And there are two more, entropy-based and first-second distance-based calibration that are used, that are making use of the rest, not just the most frequent part of the generation, but the rest of the generation as well. And you can read more about this technique in the paper. I will give a link to my slides so you can access all the papers after this talk. But the idea here is, again, very similar to what I said before. Inconsistency, even though it looks like it's something very bad, it can also be used to provide some value. Okay. And now I think some of you may have a question in your mind. There is that open field of undone research of something that is missing in the area of language models, inconsistency. And that's an important challenge. So how can you contribute individually? And I just want to say that right now in ARVA, it's AI Risk and Vulnerability Alliance that I belong to. I lead the open research projects that aims to standardize the process of consistency assessment and in foundation models and push the boundaries of research in this area in general. The main goals are to create this standard data set for evaluating consistency, to develop a set of standard metrics, to build an open, live consistency evaluation platform or leaderboard that would make use of inconsistencies and help detecting inconsistencies specifically, develop novel mitigation practices, and identify both positive and negative consequences of inconsistent models. And in this type of research, I strongly believe that when the final outcome is going to be used by a diverse set of practitioners, researchers, it makes the most of worth if the developing of these tools and of these practices and methods is also done collaboratively, getting the feedback from the diverse community. So I would encourage you all, if you are interested in the topic of the inconsistency, to contribute, to express your interest in contribution to this research. And you can do it if you are a developer, ML engineer, data scientist, ML researcher, or actually anyone who is reading the ML and NLP papers and is happy to make a contribution. You can express your interest by filling out the form, or you can contribute to our awesome LLM consistency list on GitHub as well. And that's it. That's all I wanted to speak to you about today. Please scan the left QR code if you want to get access to these slides. Please scan the right one if you want to express your interest in contributing to the project. And please contact me if you want to contact me using those links in the bottom. And now I'm open to questions. Thank you. For the form, you need to be logged in to your Google account. I hope so.
This is what I'm getting.
Oh, okay. Sorry for those technical difficulties with the form. I will change it later in these slides, and you will be able to access it.
Okay, so thank you for your talk. That was really great. I really liked how you talked about the value of inconsistency, and then actually sparked a question in my mind was, is there a risk of basically being consistently wrong as you start to train these models to be more consistent? Because it seems like the benefits are that because it has diversity, you're able to aggregate that diversity to get the correct answer. But is there, in these approaches, a check or validation step to ensure that you're not losing accuracy while you're becoming more consistent?
Yeah, that's a good question. Because yes, of course, if you are consistently wrong, it's at the very least also bad comparing to when you are just inconsistent. And because of that, it is important, I would say, it is important to use the proper metric. The metrics of inconsistency quite often use some kind of a relation to the actual accuracy. So it's not just the fact that it is inconsistent, the model is inconsistent, but also, like, is it inconsistent when it is answering correctly, or is it inconsistent when it is answering primarily correctly? So yes, the risk of being consistently wrong is also high. It's just that it is the use case when it is way easier to, which is easier to recognize. Because for being wrong, we have different metrics and ways to recognize it. And if it is wrong, like of course the methods like improving calibration or reasoning, especially reasoning, if you are just always reasoning in the wrong way, would not help. I believe that the problem with inconsistency, not necessarily, sometimes yes, but not necessarily comes from the fact that the knowledge, some kind of knowledge is not accessible to the model. If you go back to, if you remember that very first example that I showed of inconsistency with Tom Cruise and his mother, no additional data would help with that. No additional data about the fact that who is Tom Cruise and who is his mother. They will not get it. I mean, if all the data that we have additionally is about Tom Cruise and his mother, probably it will help in some way. But in general, the source of this problem is not just in the fact that a model is not, does not have access to the specific data. It's not the main primary reason of why it is inconsistent. So in terms of RAG, I think it may help a little bit, but it would not solve all the problems for sure. Sorry, there is one more person.
I have a question towards what the internal interpretation of what's happening with inconsistencies are in the embedding or latent space of the activations between two prompts. And when you're considering, is there anything that looks at the latent space representation of two inconsistent things? And does this consistency loss function and everything end up converging those at some point? But yeah, I'm not sure, I came in late, but a lot of the things seem to be only doing it at the sort of training and data phase of it, and nothing to do with sort of inside the model. Yeah.
The majority of work that was done so far was either about extrinsic consistency, inconsistency, having some downstream task in mind, and behavioral. Let's think about just behavioral consistency, which is a post hoc evaluation actually, that does not really go deep into understanding what are the intrinsic reasons of this behavior. And data, as you mentioned.
Yeah.
That's true. And I cannot think of any work that would specifically analyze how the embeddings or some latent space representations are influenced by or like influence the resulting inconsistency. If you, any of you, if you find something, a paper like that, feel free to add it to the awesome LLM consistency list. And if not, then I just hope the research like that is going to happen soon, but I'm not aware of anything of this sort.
Okay. We at